We will be beginning in 1 minute. Welcome to the Masters of Reliability webinar series. Today's topic is causes and consequences of neutral corrosion. My name is Chrissy, and I'll be your moderator for today's session. If you have questions at any time during the webinar, please feel free to enter them into the chat window, and we'll address them during the question and answer portion of the presentation. Joining us today is our expert guest speaker, Glen Bertini, President and CEO of Novinia. Mr. Bertini is a leading expert in cable reliability. He has published more than 40 articles and holds 31 patents on cable rejuvenation and related technologies. He earned a chemical engineering degree from Michigan Technological University, is a fellow of the IEEE, a voting member of the IEEE PES-ICC, and a senior member of the American Institute of Chemical Engineers. Glen, welcome, and I now turn the presentation over to you.
Thank you, Chrissy, for the kind introduction. I was privileged to participate in the IEEE 1617 writing group along with about 20 co-authors. In this webinar, we will be generally following along with the 1617 outline, but we will be adding new information, data, and some analysis that's not available in 1617. Before we begin diving into some of the information, I'd like to learn a little bit about our participants. Chrissy is going to ask you to identify which of the 5 best describes you.
All right, I'll just give everyone a few seconds to answer. Just a few more seconds. All right, I'll be closing the poll. All right.
Thank you, Chrissy. So about half of us are engineers. I'm one of those too. And one of the things that you might want to take away from this, as you'll see as we move along, is to get those craft workers to learn more about neutral corrosion. So we have a very few number of craft workers on the call, and I would encourage you to encourage your colleagues to come after the fact and watch the presentation, the recorded version of the presentation that Chrissy will tell you more about later. So our learning goals for the next about 45 minutes are to first understand the purpose of the neutral corrosion, and from that knowledge we will be able to deduce the consequences of when neutral corrosion is significant. Thirdly, we're going to seek to understand the chemistry of corrosion in lay terms. I promise I won't kill you with chemistry, but you will learn some new vocabulary today. For the first time ever, we'll see data on the extent of neutral corrosion in almost all of North America, a huge amount of data. We will learn how best to detect neutral corrosion, fifthly. And lastly, we expect to be able to understand the options that are available to you to address and deal with corrosion once it's been discovered. So let's begin with IEEE 1617, and there are basically 4 purposes for the neutral. The first is that the cable is a giant but inefficient capacitor, and hence charging current is induced on and dissipated by the neutral. The second purpose of the neutral is that if there is a fault, the neutral provides a direct return path for the fault current to the system protected devices, allowing them to trip as quickly as possible. We're going to skip 4.3 just for a few minutes. We'll be back to it in a moment. The third purpose, IEEE 1614 4.4, is to provide a return current path. Now, for well-balanced multi-phase loads, this current can be quite low, but for single-phase applications, the return current can sometimes approach the conductor current. The most common concentric neutral in underground distribution cables is composed of several copper wires wound in a helix and concentric to the conductor, covering the insulation shield. However, the neutral can come in different shapes and sizes, as seen here. Now we can circle back to 1617 4.3, and the fourth purpose of the neutral is to mitigate the consequences of a failure to successfully accomplish the other three purposes. A properly functioning neutral all but eliminates step potential and touch potential. Step potential is a difference in voltage between 2 feet, human or animal. Human step potential is low because our footsteps are quite close together, and we usually are wearing shoes with some nominal dielectric properties. Larger animals like cows or horses have a greater distance between their feet, and they don't wear dielectric shoes. An ellipsoid of zero potential will form around a damaged neutral, anchored at both vertices by a well-functioning neutral. If the distance between the two well-functioning electrodes is great enough and the soil electrical conductivity is low, the ellipsoid may intersect the surface as depicted here. This hapless cow's hind legs are at zero potential, and her front legs have a non-zero potential. If that potential difference is high enough, the cow may suffer some discomfort. Touch potential is the voltage on a cable exterior, and it's probably only recognized if you come in really close to it, such as with an accidental dig-in. So now, understanding the four purposes of the neutral, we can get a sense for the consequences if the neutral is compromised. There are 5 of them, and they're identified by 1617. The first, 5.1, is the loss of the defined path of low impedance for the flow of charging currents. This may result in the insulation shield capacitive voltage driving currents along unintended paths. These unintended currents may damage the surface of the non-metallic insulation shield with significant heating and erosion of the layer, ultimately exposing the insulation. In such cases, the result is concentrated stress, localized heating, and ultimately potentially cable failure. That is precisely what happened with the cable in the center of this frame. A microscopic inspection of the cross-section in the far right image was the result. The pit near the top is where the discharges eroded into the insulation layer. The resulting stress enhancement led to growth of a large water tree. And if you look closely near the bottom of the image, an electrical tree has formed. This is the very last step preceding a failure. The other 4 consequences include, number 2, the loss of significant neutral results in higher circuit impedance. Protective coordination can suffer, which can in turn result in more extensive damage from a fault. Number 3, the loss of significant neutral may result in charging current, fault current, and system neutral current flow on the conducting paths of adjacent metallic facilities such as water pipes. The higher impedance can also present a higher step or touch potential in connection with a dig-in and with stray system voltages. Number 4, significant loss of the neutral can result in voltage unbalances due to the uneven and elevated impedances in the neutral circuit. These unbalances can result in high voltages, low voltages, or a mixture of both from phase conductors to the neutral. And number 5, national codes might be impacted, such as the National Electrical Safety Code, commonly referred to when considering the requirements associated with the concentric neutral. The NESC does not directly discuss the neutral, but it does discuss concepts such as insulation shielding and effective grounding. The consequences of IEEE 1617 that we considered, and that we considered a consensus position of the writing group, was that the cable shield is no longer considered functional if it has experienced excessive concentric neutral corrosion. And we'll talk about what excessive is a little bit later in this dialogue. We're going to pause again, and I would ask for those of you that aren't circuit owners not to vote. But for those of you that are circuit owners, please take a look at A through E. On the A top of that list is the problems that cause your circuits to perform poorly is entirely cable. And on the bottom, it's entirely components like splices and terminations. And of course, someplace in between. So please take a vote and see what people consider to be their biggest issue.
We'll give everyone a few seconds to answer. And just a few more seconds until I close. Okay, and I will be closing the poll.
Thank you, Chrissy. So we ended up with fairly close to a 50-50 proposition. You can see that there was a similar poll done by NETRAC, and at the GCABL conference in Versailles, France in 2007, this data was presented. So NETRAC polled 22 circuit owner members and asked, in essence, the same question. And the utilities like number 21 indicated that the vast majority of their problems were associated with cable failures, whereas utility number 4 had the other way around, sort of 80% component failures and just a few percentage cable failures. And then, of course, there's everybody in between, which shared both cable and accessory failures, or about 6% were unknown. So taken together, about 55% of the failures are attributed to cable, and greater than 39% are attributed to terminations and splices, again, somewhat consistent with the poll that we just took. So let's talk about cable failures. And I have yet another poll. Again, I'd ask non-circuit owners not to participate, but for those of you that work for a circuit owner, please find the one predominant cause of cable failures at your firm, or the greatest predominant cause.
All right, I'll give everyone a few seconds to answer this poll. Just a few more seconds. All right, and I'll be closing the poll.
So you can see that our audience had water trees as about 2/3 of the cause, neutral corrosion at about 15%, and then physical damage being the next biggest piece, and then some other lesser defined issues. So let's examine what the data says, and we start with the largest systematic study that was ever undertaken to determine the fundamental cause of cable failures. It was undertaken by Dr. Steenis and some of his colleagues now at KEMA laboratory in the Netherlands. And in this study, dozens of cables were excavated from the ground and brought into the laboratory for analysis. And in each case, some of the cables had failed in service, and on this graph, those that had failed in service are indicated by a little lightning bolt next to them. And some of the cables had not failed in service. But in each case, they did AC breakdown testing, raising the voltage until the cable failed. And then the largest water tree, or the actual cause of failure, was ascertained. And this was done by having the voltage clamp down very quickly when the fault occurred, so that unlike in the real world outside the laboratory, where the actual cause of the failure is usually destroyed by the fault itself, in this case, there was a small hole blown through the side of the insulation, and the researchers were then able to determine what precisely caused the failure. And in 100% of the cases, the failure was always at the largest water tree present. So the researchers systematically searched for through the rest of the cable and were unable to ever find a water tree smaller than the one where the cable failure occurred at. So the water tree is the fundamental cause of cable failure, and just the length of the water tree has a correlation coefficient of about 78%. So there's spread in the data, of course, but at least 3/4 of the variation in AC breakdown performance is explained by water tree length. So if we take the NETRAC survey and our own survey, which is consistent with the NETRAC survey, and we take Stenis's work, we get this pie chart on the left here, which shows that water trees are the predominant, probably greater than 47% cause of failures in cables, cable systems, and components are something perhaps greater than 39% of the failures. And then we have all the other things, and it's less than 14%. So how does neutral corrosion fit into that other category? That's the primary dialogue that we're going to have for the rest of this about 30 minutes. So, and I will dive into this data more in a few more slides. But the pie chart on this graph shows the big picture. So over 81% of all the cables that we've looked at, which is 277,898 cables, have undetectable neutral corrosion. Or put another way, about 18% of the cable population has detectable neutral corrosion. These cables are the oldest cables in North America. They're the cables that the circuit owners are having difficulty with. Those are the ones that we get to see. The incidence of significant corrosion, that is where the corrosion is greater than half at a specific location within the cable, is less than 3%. So the overall neutral corrosion issue is substantially less than 3% because, in fact, many cables can operate with the significant neutral corrosion and not fail in service. They may suffer one of these other problems that we talked about, such as improper coordination of protective devices, but the actual failure rate caused by corrosion is going to be much less than 3%. So now let's examine the fundamental causes of corrosion, and IEEE 1617 identifies 5. The first one is galvanic corrosion. It involves the flow of positive ions off the surface of the metal at the anode. These ions typically combine with negative ions existing in the environment at the surface of the anode to form an oxide. Corresponding to the loss of positive ions from the surface of the metal is the release of negative electrons. Electrons, of course, flow in the metal toward the anode region, away from the cathode region, where they can continue with positive ions existing in the environment. Each metal or alloy has a characteristic electrochemical potential. When you arrange each metal by that potential, you get the galvanic series shown in this chart. The most anodic materials are on the top, and the most cathodic materials are on the bottom. If you, for example, bonded copper neutral to steel rebar of a volt, the copper will not suffer galvanic corrosion because the steel will sacrifice itself because it's higher on this chart. Copper is very cathodic, and it's unlikely to be connected to stainless steel, which is below it in the chart, silver, gold, or platinum. So the more anodic materials will in fact sacrifice themselves to protect or mitigate corrosion on their cathodic bonded cousins. We will come back to sacrificial anodes later in this webinar, but notice that magnesium and zinc are on the top of this anodic list, and these are the materials of choice for sacrificial anodes. There are 4 other causes enumerated by 1617. Number 2 is the corrosion of a single piece of metal occurs when there's potential differences established along its surface. Little defects like knife cuts or mill scale, scratches, or microscopic inclusions, each of these locations will have a slightly different electrical potential, and therefore there's an opportunity for corrosion. Number 3, there's potential differences that exist when a cable passes through 2 different soil types. For example, acidic soil and alkaline soils. Number 4 is there can be differences in soil oxygen content. This results in differential electrical potential. A bare cable passing from a clay soil of poor aeration into a gravel soil of greater aeration will form a differential aeration corrosion cell, with the soil of low oxygen content becoming anodic, and of course the other side becoming cathodic. Another common situation that causes differential aeration is where a cable goes into a conduit for a short run, such as under a street. The fifth cause, enumerated in 1617, are stray electrical currents. They're typically from nearby DC sources such as arc welding machines, impressed current cathodic protection systems operating on adjacent foreign structures, transit systems, and so forth. One example I experienced in Georgia was a natural gas pipeline that had active cathodic protection, and it destroyed the neutrals on the adjacent power cables. Each of these 5 corrosion causes, however, requires 5 elements to occur. These 5 elements are A, a chemical potential which induces a relatively positive charge, which is the anode, and B, a chemical potential nearby that induces a relatively negative charge, the cathode. C, the neutral must still be intact. D, the soil must be moist in order to transport ions. And E, there has to be an oxidizer, such as water or elemental sulfur. Let's talk briefly about oxygen, because oxygen is by far the biggest oxidizer that neutrals have to deal with. The concentration of oxygen generally declines as you go deeper in soils. This is because plants and animals use the oxygen as it diffuses from the atmosphere. Worms, insects, plants, bacteria, and fungi extract oxygen. There's good news and bad news about this. The good news is that lower oxygen concentrations reduce the rate of corrosion. The bad news is that this reduction with depth is not likely to be perfectly uniform. Differences in aeration along a cable length may lead to corrosion by this differential aeration mechanism. The depth at which the soil becomes anaerobic varies widely. In wetlands, it often occurs within inches of the surface of the soil. In grassy uplands, the boundary may be several meters deep. If a cable passes from a wetland into an upland, differential aeration is almost a certainty. To understand the impact of oxygen on degradation mechanisms, consider that the extinction of mastodons occurred almost 11,000 years ago, yet excavations of their corpses sometimes yield virtually intact organs and other soft tissue. The reason that these soft tissues remain intact is because they're found in anaerobic soil. That's science speak for swamps, bogs, and shorelines. Just as anaerobic conditions protect ancient remains of these hairy beasts, they also protect bare concentric neutrals buried in swamps and near marine estuaries when the whole of the cable lies in stable anaerobic conditions. Returning now to our 5 identified causes, let's focus on the really important ones. Number 1, galvanic corrosion only occurs where copper is bonded to a more cathodic metal. This should be avoided for sure, and it's a rare occurrence. Number 2, single metal occurs, but it's insignificant. It results in minor pitting on the surface of the cable. Jumping down to number 5, stray currents are rare, except in the example I gave you before, where you have some kind of active cathodic protection on neighboring structures. So it turns out that 3 and 4 are the main drivers for significant neutral corrosion, the kinds that cause problems for us. Here are 2 hints from this realization that you can use. Number 1, to avoid soil corrosion, use native backfill on pit restoration. If you put in select backfill, you're changing the chemistry of that soil. Number 2, to avoid differential aeration, also use a native backfill and make sure you compact it. That's how you can avoid those 2 things. So we get now to another fundamental and really important question. Now that you understand the basis of how neutral corrosion works, let's see if we can surmise how neutral corrosion is likely to progress with time. So we're going to do a thought experiment. Imagine that you excavated a cable after 20 years in service and that 40% of the neutral was gone. So we're able to look at 2 data points on the graph. We know that when the cable was brand new, i.e. it was 0 years in service, that it had 0 corrosion. And we know that 20 years later, 40% of the neutral was gone. I'm going to provide you with 3 curves, and we're going to ask you to choose which one you think probably represents the way that corrosion is likely to proceed on a going forward basis. So the first choice is it linear? Is it straight line like that? Does it have an increasing slope? Or choice C, is it a decreasing slope?
All right, I'll give everyone a few seconds to answer this poll. Just a few more seconds. All right, and I'll be closing the poll.
So a little bit more than half guess that there'll be an increasing slope. About only 4% think it's linear, and about 40% think that the slope is decreasing. So now I did promise you there'd be a little bit of chemistry. So let's talk about the chemistry of this situation. And we've already seen what is required in order for neutral corrosion to occur, these 5 items in the lower right-hand corner. So imagine you have shiny new neutrals freshly buried, and the soil on the left is slightly acidic, and the soil on the right is slightly alkaline. The difference in hydrogen ion availability establishes a potential difference between the right and the left, an anode and a cathode. There is a metallic connection between the anode and the cathode, the brand new neutral. So we've met the first 3 requirements right off the bat. But the soil is wet, so it facilitates the transport of ions through the soil. So we've met the 4th requirement. But it's not so wet that the soil is anaerobic, so there's some oxygen present. If the potential difference between the anode and the cathode is greater than the electrical chemical threshold for oxidation of copper, corrosion will begin. So we're going to assume that that's the case. Now we want to examine how that rate of corrosion would proceed. And it's going to be, the rate's going to be determined by our old E equals IR equation, which I've rearranged, because the current flow, how much current actually occurs, determines how much corrosion there's going to be. Let's examine the factors that determine the electrical potential first, the numerator, if you will, of that equation. First, there is no oxidation unless the E is greater than the threshold required to drive the electrochemical reaction. If the potential is not high enough, there will be no reaction. Second, the flow of current, if present, reduces the acidity of the soil on the left. It's like a battery. There's only so much electrical chemical potential in the soil, and using the battery depletes its charge. To recharge the battery requires new molecules from outside the system to provide fresh fuel. For differential aeration, the fresh fuel is oxygen diffusing into the soil or conduit. For non-differential aeration, it requires that you add some new fuel like fertilizer, so that requires people to change something on a soil surface. Aside from these recharging cases, the E is going to decline over time. That means that the rate of corrosion will decline over time. The third element there is entropy. And entropy is also called the second law of thermodynamics, and it works to equalize the hydrogen ion concentration in our example soil. Excess protons in the acidic soil would be transported to the alkaline soil. This is the same as a battery. It discharges itself even without a load. Entropy causes the voltage to decline over time. So all 3 of these factors reduce the E over time. Now let's look at the denominator of the equation. That's the R. How does it change over time? When the copper neutral is shiny and new, there's very little resistance between the copper and the wet, compacted soil. However, as corrosion occurs, a thin layer of typically green copper oxides and copper carbonates form. We can see the lovely patina on the copper neutral along the left border of the screen. These copper oxides and copper carbonates are not conductive. Their formation increases the resistance of our loop. An increase in the denominator of the equation decreases the current I, and hence the rate of corrosion. In addition to its resistance to the flow of electrons, it also impedes the transport of oxygen to the native copper below, reducing the electrochemical potential further. If the potential difference drops below a certain threshold, then corrosion ceases entirely. Finally, there's one more effect on the resistance. There's the resistance of the neutral itself. As the neutral is consumed, the resistance of the loop increases. When individual strands are severed, the corrosion on those strands all but stops. This is why neutral corrosion is a consistently confined phenomena. When we excavate neutral corrosion sites, the damage to the neutral is most typically concentrated within just a couple of feet. I'll describe an exception to that in an example a little bit later on. But all 5 of these factors reduce the rate of corrosion as time advances. I want to refine the definition of patina for a moment, and then we'll return to the neutral corrosion causes for the conduit case. So let's talk about the patina. The patina is a thin crust that forms on the surface of many metals. In the case of copper, there are a variety of oxides, hydroxides, carbonates, and even some others. The colors can range from familiar blue-green to black and red. This sample has 3 different oxides. All are non-conductive, and all inhibit the transport of oxidizes to the native copper underneath. And most of them are very stable. The patina on this copper roof, which was installed in the middle of the last millennium, endured unscathed well into the 20th century until the widespread burning of high sulfur coal led to acid rain. Acid dissolves copper carbonates, acid soil dissolves copper carbonates. So let's consider now the case of cable in a polymeric conduit. In the illustration, we consider the specific case where there's a dip in the conduit, which is partially flooded with water. The illustration is a simplification of real-world conditions, of course, because the water is not going to be clean. In fact, each time water enters the conduit, it carries silt and sediments. Those solids tend to settle in the low spots in the annular space between the cable and the conduit. This silting can sometimes interfere with cable removal, but we're interested in the silt because it provides an important equivalent to soil in the direct buried case. If a bare concentric neutral cable were in a clean plastic conduit, there would not be an environment for ionic transport outside of the puddle. The silted conduit bottom wicks water against gravity outside of the puddle and potentially provides an environment for water and ions, a requirement for macroscopic corrosion to occur. Let's blow up the right side of the illustration to take a closer look at what might be happening. The corrosion mechanism is identical to the direct buried case, except that because the water level changes with the seasons, the anode and cathode move with the seasons. Corrosion is likely to be more distributed along the length of cable than with the direct buried case. This is the exception I mentioned earlier. So now we're ready to answer this question with a little bit more authority. The right answer is decreasing, and we'll show you some data later that validates this theoretical expectation. We're going to take a pause sort of in the middle of this dialogue to see if there are any questions that we want to address before we move on to the next major subject.
Thanks, Glenn. We do have one question coming in here. Ryan asks, is it possible to determine the amount of neutral degradation in outer concentric secondary cables? Most cables are either 4/0 or 1/0 with bare copper neutral, approximately 20 strands, wrapped around 2 insulated conductors. The span lengths average between 60 to 70 feet. If possible, what methods and equipment would be used to determine percent neutral remaining?
Well, that is an excellent question, and we are going to address it slightly coming up a little bit later. But the primary focus of our dialogue has been primary cables, not secondary cables. And as you'll see when we start talking about how to identify and correct neutral corrosion on primary cables, we're going to end up focusing on time domain reflectometry as the best way to do that. But with secondary cables, TDRs don't work very well. They can work, but they don't work very well. And that's because the concentric arrangement of a primary cable is well suited to a TDR. So when it comes to secondary cables, the answer is yes, you can. And the right way is with a resistance measuring device like, I'll show you a picture of one later, called an ohm check, for example. So we'll get, if I haven't completely answered your question, you can sort of re-ask it after we've looked at some other examples.
All right, thank you. And we do have time for one more question. When one strand of concentric corrodes through, corrosion on it may stop, but doesn't the current then pick up on the remaining strands, increasing corrosion on them?
Yes, of course. And again, we'll see some real data on this coming up a little bit later. But remember, corrosion is occurring on a very local level. So as soon as I break the strand, now whatever current was flowing through that strand has to go through additional soil and additional tortuous paths in order to move on to the adjacent neutral. So as you start to lose neutrals, and you'll see we find significant corrosion. We already saw the graph earlier, about 3% of the time, that it's not unusual to have 50% of the neutrals corroded. Not unusual in the sense that it happens about 3% of the time in North America. But you're right, it'll divert onto another path.
All right, thank you. Back to you.
All right, so now I'm going to show you a series of photographs. And first I'm going to show them really big, and we're going to test your knowledge again here. And so we're just looking at these photographs, and the question is very simple. Is there evidence of neutral corrosion, yes or no? I'm going to show you 4 photographs, and then I'll put all 4 photographs on a single slide. So here's number 2, a jacketed URD cable. Is there evidence of corrosion there? Number 3 is a helicoidally wrapped tape cable, also with a jacket. Is there evidence of corrosion there? And the 4th one is we have a URD cable with holes in the shield. Is there evidence of corrosion there? And so Chrissy is going to see if you can select all that apply. This time you can vote for more than one.
I'll give everyone a few seconds to answer this. Just a few more seconds. Okay, and I'll be closing the poll shortly here.
So we have an astute crowd. We can see that all 4 cases, there's evidence of corrosion. It's maybe the hardest to see in number 4, but all 4 of them have significant neutral corrosion. So then I changed the question around, the same 4 pictures. And this time the question, now that we understand the purpose of the neutral, the question is, does the corrosion interfere with that purpose? And so the same 4 pictures, and I'll remind you here what the purpose is, the same 4 pictures assess whether or not those 4 cases interfere with the purpose of the neutral. So I'll get all 4 pictures up there, and then we'll get Chrissy to check with you again.
In just a few seconds for answering this poll. Just a few more seconds. Okay, I'll be closing the poll.
So we have a pretty clear understanding that when there's holes in the cable caused by neutral corrosion, that's a serious issue. And about 1/3 to 40% thought that the other ones were significant enough to interfere with the purpose of the neutral. And I didn't do a good enough job, apparently, of explaining the purpose of the neutral because none of those 3 cause any problems. The discoloration is a normal situation with copper. It's the patina that protects the copper. It's only when the neutrals are actually severed or broken that it actually causes a problem. One of the reasons that I think that we struggle in the industry with neutral corrosion is that we often ask our line personnel or technicians to determine if the neutral is corroded when they fill out a failure ticket. Or maybe there's not even really a ticket, but there's dialogues that occur between the engineers back in headquarters and the line personnel that go out. And the question that's usually asked is there corrosion on the cable that you saw that was faulted? And the answer is almost always yes, because you can't bury a clean piece of copper in the ground without it getting that green color. So the correct question that we should be asking is the corrosion of the neutral of sufficient severity to have caused this fault? And I hope it's becoming obvious that in order to answer that question, that there's some knowledge that's required on the part of the person making the assessment to understand the purpose of the neutral and to be able to make that judgment. So I think very frequently what happens is people answer the question, yes, the neutral is corroded, but they don't ask, they're not able to answer the real question, is it significant enough to actually cause an issue? So another poll is to find out which of the following best explains why neutral corrosion is so over-reported. We saw about 20 slides ago that only 3% of the cables in North America have corrosion that causes a problem in the function of the cable. In our audience here, we have people suggesting a really high level of problems caused by kind of minor corrosion. What do you think explains why we're over-reporting and over-emphasizing neutral corrosion?
I'll give everyone a few seconds to answer this poll. Just a few more seconds. All right, I'll be closing the poll.
Okay, so about 2/3 said all of the above. I would concur with all of the above. And about 1/3 thought that was a lack of understanding. So of course that's true. And I think A and B are both also proper answers, because pretty much any time you dig up an old cable, it's got that green look to it, and it doesn't look like a brand new cable. So people just assume that it's not functioning properly, which is kind of B. And then letter C is, because these cables are buried, it's kind of easy to assume the worst case. And when we do actual work where we dig cables up, the cables are almost always that green color, but they're not of sufficient severity to actually cause problems. So I think all four are significant reasons why we have an emphasis on neutral corrosion issues. Now let's turn our attention to an assessment of the significance of neutral corrosion. This is an intriguing map that I found. It was produced by the U.S. Department of Agriculture, doing a very extensive soil survey of the United States. The map was prepared for ground penetrating radar, and the properties selected to prepare this map include clay content, mineralogy, electrical conductivity, soil absorption ratio, calcium carbonate levels, and calcium sulfate contents, and a variety of other things. They weren't trying to determine where neutral corrosion would be the worst or the best. They certainly didn't have data at all. But there's an intriguing correlation between this ground penetrating radar data and neutral corrosion. And I can tell you that if there was sufficient interest, we would be able to do some more work with the scientists at the USDA, because they have the data broken down into individual components. And some of the components that they have aren't going to be significant in determining corrosion, and others are. And so we could do a better correlation. But even without that kind of refinement, this map gives you some sense of where neutral corrosions occur or not occur. So first, we take the macro view of the lower 48 U.S. states. In the next sort of about a dozen slides, we're going to go through groups of states and provinces, and we're going to have to go through them fairly quickly. Remember that these same graphs are available in the companion paper to this webinar, so that you can study them at your leisure, because you're going to want to look at your individual states. Furthermore, higher resolution GPR state maps are available at the web address shown on the bottom of this slide, and also linked to on the page that we'll show you later. For each pie chart, the political boundaries are defined, and the number in parentheses represents the number of cable segments in the tested population. Light green is undetectable corrosion level. Dark green is detectable but not significant. Bright red and dark red are where corrosion is an issue. and the bright red is significant corrosion, and dark red is the really, really bad corrosion where almost all the neutrals are gone. So now let's take a look at some of the state-by-state sort of view. California suffers an anomalously high corrosion rate. I believe primarily because California was an early adopter of cable and conduit. And as we described earlier, cable and conduit creates an environment where differential aeration is more common than in direct buried situations. The Rocky Mountain states have below average incidences of neutral corrosion. The Central Plain states are about average, except slightly higher in Nebraska and Kansas. However, Kansas has a very small sample size, and the results are not statistically significant. The Midwestern Plains enjoy less corrosion than average, except for some narrow geographies within Wisconsin and Minnesota. The Eastern Midwest through the Mid-Atlantic states have a very low rate of neutral corrosion. Another note of statistical insignificance is the Mid-Atlantic states, the sample size there is very small because the Mid-Atlantic states have solid conductor cables, so my firm doesn't do nearly as much testing there as we do in other states. The Southeastern United States also has very low neutral corrosion incidence, except perhaps in Tennessee, where the incident rate is above average. As we move into the Northeast, the rates are generally greater than the national averages. And finally, as we move to the very tip up there, above Massachusetts, where the corrosion is unfavorable, the rest of the states north of that are quite favorable. And then our last graph, picking up Alaska and Hawaii and Canadian provinces, the big one that stands out is British Columbia. It has quite a high neutral corrosion rate, but the rest of Canada has a very low corrosion rate, and then a slightly higher rate in Hawaii, presumably due to the volcanic soils there. So that's what the data says, and that's over 150 million feet of cable, state by state, and of course we have it even in greater granularity, but giving the sort of big picture. Now, in 1994, the ICC task force, that was the forerunner by IEEE 1617, published a 7-year survey of circuit owner reported neutral problems. There was also a 5-year period where that survey overlapped with a similar survey called the AEIC Cable Report. In this table, we put the two reports side by side and compare the reported incidences of cable failure to the reported incidences of neutral problems. The ratio of this to failure rates varies on the bottom line to between 10 and 25x. Neutral corrosion is at least 10 times less significant than cable failures. This table was published by Bob Gurniak of Pennsylvania Power and Light in T&D World in 1996. Let's turn our attention now to how neutral corrosion can be detected. 1617 lists 4 methods to detect neutral corrosion. Visual inspection, not very good for direct buried cables and not even very good for cable and conduit because you can't really see the cables. TDR is by far the most common method used. Resistance measurements, as I alluded to earlier, are also used. They can't pinpoint the corrosion, but they can tell you whether there's corrosion or not. Surface voltage measurements is a method that was used in Wisconsin in particular for a short period of time, but there's no commercial implementation of that basically because it's too expensive to implement. And for the balance of this section, we're going to talk about the TDR, which performs more than 99% of all neutral corrosion survey work. So here's how we use the TDR. And this is included in 1617. A thorough step-by-step explanation of how to use the TDR are described publicly on my firm's website, and we'll give you the reference to get to that a little bit later on. The TDR transmits a narrow, low-voltage pulse, about half the speed of light down the length of the cable. The low voltage is about 20 volts. A device called an impedance streamliner facilitates a smooth transition from the impedance of the coaxial cable to various coaxial power cables. The streamline transition minimizes the reflection, attenuation, and dispersion of the signal as it enters the subject cable. The use of the streamliner improves the sensitivity and accuracy of the measurement. Where splices are present, the cable has a characteristic S wave. Impedance includes resistance, capacitance, and inductance. In the case of a splice, the neutrals are trained away from the conductor, which reflects a positive wave because the impedance increases. The subsequent negative wave is a result of the neutrals returning to a position closer to the conductor, decreasing the impedance. Where there is neutral corrosion, the resistance increases and the capacitance decreases, but the former dominates and a positive wave is created. The capacitance effect is generally too small to observe. Finally, at the far end of the cable, a ground is applied and the resistance is close to zero. The TDR will provide the distance from the termination to the corrosion position and the extent of that corrosion using the relative heights of the reflections as shown in Table 1 of P1617. In our example, the height of the neutral corrosion pulse is less than that of a typical splice, so the neutral corrosion level is a 2. To pinpoint the precise location of corrosion, a radio frequency tone is applied to the conductor, and the return tone is urged onto the neutrals with a jumper as shown in the image. Much of the resulting electromagnetic field is canceled where the neutrals are in good condition. This occurs because the neutral return is 180 degrees out of phase with the conductor supply. Of course, where neutral wires are broken, this cancellation is compromised. As a consequence, the neutral corrosion location sings loudly. An operator with a receiver walking over the cable can pinpoint the precise location of the corroded neutral. The equipment and procedures for doing this are available publicly on our website. It's useful to pinpoint the location of this corrosion because it is possible to repair the corrosion. IEEE 1617 has basically 2 suggestions to address neutral corrosion. Number 1 is you can repair it and provide cathodic protection, or you can replace the entire cable. To repair it, a pit is excavated over the corrosion site. Normally, the corrosion site is just a few feet long. New neutrals are wrapped tightly around the cable and clamped into place with special clamping hardware. The clamps also have dedicated lead to a sacrificial magnesium anode. The anode is bedded in bentonite clay within a linen bag. Normally, when cathodic protection is applied to protect underground structures, placement of a sacrificial anode requires much consideration. But when doing a neutral repair of a decades-old cable, the optimum location has already been determined for us by history and reinforced with the disturbance of the soil required to excavate the pit. A post hole digger or auger is used to get the anode several feet away from the repair site. The bag can be placed at a length or depth below the cable, at the same depth, or anywhere in between. So we've learned 5 or 6 things. First of all, the purpose of the neutral is the system return and to bleed excess charges and to relieve fault currents. We learned that when corrosion is excessive, grossly excessive, that it causes coordination problems, quality issues, potential safety issues, and in extreme cases may even cause faults. We learned the causes of neutral corrosion that are primarily differential aeration and soil chemistry changes, and we learned that all of these factors that affect corrosion decrease with time. We learned that overall the significance of corrosion is less than 3% of the population of cables, and we learned that we can detect it with TDR and other approaches. And finally, it's possible to fix neutral corrosion because it's often very localized. The website that you might go to for additional resources is listed on the bottom of this page. And at this point, we'll see if there's any additional questions that I can answer before we call it quits for the day.
All right, thank you, Glenn. We have received some more questions from our audience. And to answer one question that we hear a lot, yes, a recording of today's presentation will be available afterward on Novinium's website. The first question we have comes from Eric, and he asks, most power cables have oversheaths. Should we consider that neutral corrosion happens no matter the jacket is hermetic after installation process?
Well, there's a whole bunch of questions inside that one question. First of all, we saw some images in the presentation of cables that had jackets that had corrosion underneath. Many modern jackets encapsulate the neutral, so there's no space for water to accumulate underneath the jacket. And of course, people are going to make attempts to seal jackets with even non-encapsulating jackets to seal those with mastics at the splices and terminations. But water is a very tenacious material, and it ultimately finds its way into every nook and cranny. And also water diffuses right through jackets. So at the end of the day, any exposed copper is going to become corroded in the sense that it's going to have a patina. The only problem is if that patina gets eroded off with acidic soils or some other way to take the patina off. As long as the patina is present, the cable will function just fine. So compared to direct buried cables, which the majority of the cables that we've been talking about are direct buried bare concentric neutral cables, those cables that have shields or jackets, over the neutrals are going to have much less of a neutral corrosion problem in general. Hopefully that answers your question, Ryan.
Thank you. And our next question comes from Corey. He asks, we perform online partial discharge testing to help determine cable problems. How does neutral corrosion affect this test? We have CLX cables with tape shields.
Well, there's a couple of possibilities. And again, a lot depends, Corey, on the extent of neutral corrosion. So most of the service providers that do neutral corrosion detection, that do partial discharge detection, also do a neutral corrosion test in advance. In the example that we saw 20 or 30 slides back, where we had actual discharges from a bad neutral to the insulation shield, one would be able to correlate the TDR result. Let's say it said that there was neutral corrosion 220 feet from the end of the cable, and then if the PD result said there's PD 220 feet from the end of the cable, you'd be able to correlate that that PD probably, or you'd have a good sense at least that the PD might be associated with that neutral corrosion. The other problem that corrosion does in general is it attenuates signals. So PD measurements are all trying to make very sensitive picocoulomb or very low level measurements. And if signals being attenuated by corroded neutrals, that can make the testing a lot less sensitive. The even worse case is if you have wrap tape concentric neutrals, the spiral tape ones. A small amount of corrosion there really quickly attenuates the signals and pretty much makes PD testing not possible. Good question, Corey.
Thank you. And our next question comes from Josh. He asks, how did you establish the correlation between TDR pulse height and severity of neutral corrosion? Doesn't the location of the corrosion signal on the cable affect its height?
One of the reasons, Josh, that we are so careful with our impedance streamlining device, also called an impedance transition device, is to make sure that we have a nice clean signal going into the cable. Of course, as that signal goes along the length of the cable, it's being attenuated and getting smaller and smaller. But then it reaches the end of the cable ultimately and reflects back. So we have an automatic calibration on the end of the cable of how much signal is getting back from the far end of the cable. So if attenuation is higher on cable A than on cable B, we're looking at relative heights of peaks. So that's how we solve the attenuation dispersion issue, is by using relative measures. The first part of your question was, actually, would you repeat the first part of the question, because I forgot what it was.
Yes. How did you establish the correlation between TDR pulse height and severity of neutral corrosion?
Right. So we dig up corrosion sites quite frequently. We started, of course, in a sort of a laboratory environment. We did it at the NETRAC laboratory in Georgia Tech. And in that case, we were testing in sort of a side-by-side test with the ohm check device, which is measuring the resistance. And then we did a neutral corrosion TDR, and there was known corrosion. And the TDR accurately found the percent corrosion just as the ohm check did. They both basically gave the same result. And then besides that single test at Georgia Tech, we've excavated many cables over the course of testing and treating over 150 million feet of cable. And so we look for that correlation each time we do that.
Thank you, Glenn. Our next question comes from Steve. He asks, can neutral corrosion cause arrestor failure or failure of the arrestor to work?
I can't imagine how it would cause arrestor failure, but it could definitely cause the arrestor failure, the arrestor to fail to operate properly. You're attempting to take a fairly narrow pulse, high voltage down the length of the cable, and when it's reaching the arrestor, it's been attenuated and dispersed by any impedance changes along the cable. So if your corrosion was significant enough, you would be decreasing the extent of the voltage and so forth when it hit the arrestor. So it would hamper arrestor usage. On the other hand, the fact that the corrosion was there attenuated the signal, which means that it's doing the same thing that an arrestor does. So it's probably not that big of a deal, other than the potential for stray current right when the lightning strike occurred.
Thank you, Glenn. Another question comes in from Matthew, and he asks, are the effects for aluminum cable similar to the effects on copper cable that we discussed?
I wonder if he means aluminum stranded cable where it's the conductor, or if we're talking about aluminum neutrals, which I have, so I'll answer both questions. Aluminum neutrals are really rare, but it was done in the early 1970s, late 1960s, and it was a disaster. So bare aluminum cables, the oxide that forms is sort of readily taken away by soil chemistry, and it takes only a couple years before the aluminum neutrals are completely destroyed. So I've only seen that in 150 million feet of cable like once or twice. So I'm assuming that you're talking about the aluminum in the center of the cable that's carrying the current. And you can have pretty significant corrosion. We see it quite frequently, especially in near marine environments where you have saltwater intrusion from hurricanes and so forth. A substantial amount of aluminum hydroxide formed. But there isn't enough oxygen present for it to go too far, and it doesn't get affected by the outside soil chemistry. So once the aluminum oxide forms in a primary cable, it's pretty stable and doesn't seem to interfere with the operation of the cable, save one exception, which is at the terminations where you have to make a connection that is compatible with a compression connector and meet ANSI C119.4. So there can be problems with corrosion where you make a termination, but I've never seen any significant problems in a primary cable within the cable itself where it causes any kind of operational issue. That's primary cables. We had a question earlier about secondary cables. Different story altogether. If you have a cut in the insulation of a secondary cable, letting water in, this is a completely different subject than the subject that we're talking about here, but water in secondary cables causes huge corrosion problems and can cause the cable to fault.
All right, thank you, Glenn. Our next question comes from Omar. He asks, when corrosion is detected, do you replace the corroded section of the cable or the entire cable?
Yeah, Omar, the cable is fine. I mean, of course, the choice is the utilities to make. They can choose to replace the entire cable if they want. But when we make a corrosion repair, as I mentioned in the body of our dialogue, that typically just 2 or 3 feet of cable are corroded, and then it's fine on either side. So we wrap some clean copper neutral around that spot, clamp on, and we basically just replace the neutral. And as I mentioned, also we drop a sacrificial anode in there to protect it on a going forward basis.
Thank you. And another question, Mike asks, at what level of concentric neutral corrosion will insulation shield damage occur?
So the one photograph that I showed you, I'll actually go back to it, is the only one that we've ever seen. So we see a large number of faults and corroded cables. And in this one, there was no neutral at all. So it was 100% neutral dissipated. The other thing that has to be true to cause the fault is the insulation shield itself has to no longer function the way it was designed to function. So in this example right here, I don't remember the exact number off the top of my head, but the insulation shield resistivity has a specification, an AEIC specification, and let me just guess that it's something like 2,000 ohm centimeters. And this one was 10 times higher than that. So it was way outside the allowed limits. So it takes not only a substantial loss of neutral, like 75 to 100% neutral corrosion, but it also requires a degradation of the insulation shield, which is not a situation that you normally find, and to find both of them together is very rare. This picture is the only one that I know about in the world.
Thank you, Glenn. We have time for one more question. Josh asks, have you seen significant corrosion in jacketed cable systems?
So again, the word significant needs to be defined. I think in all cables have some level of corrosion. I've seen some encapsulated jacket cables where there's no airspace, no water space, if you will, between the conductor and the polymeric material, and they're corroded. Oxidation occurs at the surface, you get the green color and so forth, but there's no degradation in performance whatsoever. So I'll take the word significant to mean where it significantly impacts the operation or safety of that cable. And the answer is it occurs occasionally, but not very frequently. And where it occurs is on non-encapsulating jackets that have significant water ingress from jacket destruction, like if it was dug into or during construction, if there was big rocks that cut through the jacket. So where you have lots of water flowing in, then it's just as bad as being buried in the soil.
All right, thank you so much, Glenn, for taking the time to speak with us today, and thanks to everyone for joining us. If we were unable to answer one of your questions today, we will make sure to reach out to you. We hope you enjoyed the webinar, and we look forward to the next Masters of Reliability webinar scheduled for September 27th, featuring Dr. Richard Brown. Dr. Brown will share the importance of engaging regulators and commission staff when addressing aging infrastructure, as well as the justification of proactive rehabilitation programs. Dr. Brown is a principal engineer with Exponent and director of its engineering management consulting practice. He has provided consulting services to many major utilities in the U.S. and has submitted expert witness testimony to regulatory commissions in 8 states. Registration is now available on the Novinium website at novinium.com/webinars. Thank you, everyone, for joining us today.